Coming to the first question. In figure 9.15, ABCD is a parallelogram with AE perpendicular to DC and CF perpendicular to AD. If AB is equal to 16 centimeters, AE is equal to 8 centimeters and CF is equal to 10 centimeters, find AD. Now moving on to the solution. Let us note down the given information that ABCD is a parallelogram. We know that in parallelogram, opposite sides are parallel and are equal. Therefore here, AB is parallel to CD and AB will be equal to CD. Similarly, AD will be parallel to BC and AD will be equal to BC. Here, the given lengths are AB is equal to 16 centimeters. Therefore, CD will be also 16 centimeters and AE is given as 8 centimeters and this is perpendicular to CD and CF is given as 10 centimeters and this CF is perpendicular to AD. Now we know the area of parallelogram formula as product of base into corresponding height. Here two perpendicular distances are given, that is CF perpendicular to AD and AE perpendicular to CD. Therefore, we can consider here the base of the parallelogram while finding the area as DC and also AD. Therefore, area of parallelogram with base as CD, that will be equal to base into corresponding height. Here the base is CD and corresponding height to CD is AE, which is equal to CD is given as 16 centimeters and AE is given as 8 centimeters, that is equal to 128 centimeters square. Now let us consider the area of parallelogram with base AD. That will be equal to, here the base is AD and corresponding height is CF, that is equal to AD value we need to find and CF is given as 10 centimeters. Area obtained in both the cases must be equal since it is the area of common parallelogram ABCD, that is AD into 10 centimeters is equal to 128 centimeters square, which implies AD is equal to 128 centimeters square by 10 centimeters, which will be equal to 12.8 centimeters. Therefore, the length of side AD is 12.8 centimeters. Moving on to sixth question. A farmer was having a field in the form of parallelogram PQRS. She took any point A on RS and joined it to the points P and Q. In how many parts the field is divided? What are the shape of these parts? If the farmer wants to sow wheat and pulses in equal portions of field separately, how should she do it? Now moving on to solution. Let us consider a PQRS parallelogram which is in the form of field, that is as shown, and he says that she took a point A on RS. Let us assume a point A is taken on RS and later she joined it to P and Q. Let us join AP and AQ. Then it forms a triangle APQ. Now here the triangle formed APB and now here the triangle formed, that is nothing but APB, that is nothing but APQ, and here initially we have a field in the shape of parallelogram, that is PQRS. These both lie about the common base PQ, and they also lie about the common parallels, that is PQ and RS. We know that if a triangle and a parallelogram lie about the common base and between the common parallels, area of triangle will be equal to half times area of parallelogram. Therefore, here we know area of triangle APB will be half times area of parallelogram PQRS. Therefore, as area of APB is equal to half times area of PQRS, here the area of remaining part in the parallelogram, that is area of PAS plus area of RAQ, will be equal to half times area of PQRS. He says that she want to show the weight and pulses in equal portions of field separately. How should she do it? So let us divide the parts. That is, if pulses are grown in the area of triangle APB, then weight can be shown in remaining portion, that is in the area of area APS and area of AQR. And also similarly, if weight is grown in APQ area, which covers the half of the parallelogram, then pulses can be shown in remaining area, that is area covered under triangle APS and AQR. Moving on to second question. If EFGH or respectively the midpoints of sides of parallelogram ABCD show that area of EFGH is equal to half of area of ABCD. Now moving on to the solution. Let us consider a parallelogram ABCD with midpoints EFGH on the sides AB, BC and CD respectively as shown in figure. Now we are required to prove that area of EFGH is equal to half times area of ABCD. So in order to prove this, let us initially join EF, FH, HG and EG and also join EH. We know that in parallelogram AD is parallel to BC since opposite sides are parallel and are also equal, which implies as E is a midpoint of AD, we can write AD as 2 times AE is parallel to BC is parallel to AD, and now we know that H is a midpoint of BC, so we can write BC as 2 times BH, which implies AE is parallel to BH, and also we know that EH as passing through the midpoints of AE and BH, EH also will be parallel to AB, and here AE HB is a parallelogram. Here if we consider ABEH as a parallelogram, and EFH is a triangle in it, here both the parallelogram and triangle lie in between two parallel lines AB and EH, and also they have common base EH, we know that area of triangle is half the area of parallelogram when they both lie about the common base and two common parallels. Here, the parallelogram EFGH and triangle EFGH lie in between the two common parallels, that is AB and EH, and they lie about the common base EH. Therefore, we can say area of triangle, that is EFH, is equal to half times area of parallelogram, that is AEHB. Similarly, if we consider parallelogram EHCD, we get area of triangle EGH is equal to half the area of parallelogram EHCD. Let this be as equation number 1 and this be as equation number 2. Now adding 1 and 2, we get area of EFH triangle plus area of triangle EGH is equal to half times the area of parallelogram AEHB plus area of parallelogram EHCD. That is, here area of triangle EFH and area of triangle EGH is equal to the area covered under the figure EFGH, which is equal to half times area of parallelogram AEBH and area of parallelogram EHCD gives the area of total parallelogram ABCD. Therefore, finally we can say that area of EFGH is equal to half times area of parallelogram ABCD. This is what our required proof, and it is hence proved. Moving to question number 3. P and Q are any points lying on the sides DC and AD respectively of parallelogram ABCD. Show that area of triangle APB is equal to area of triangle BQC. In order to prove this, let us move on to the solution. Now, considering the parallelogram ABCD, in this he says that P lies on DC. So let us represent that point P, which is lying on DC, and Q lies on AD. Let us also represent the point Q somewhere on AD. He asks us to show that area of triangle APB is equal to area of triangle BQC. Let us represent both the triangles in the figure, that is triangle APB. Let us represent the triangle APB in the parallelogram and also triangle BQC. So initially we represented triangle APB and triangle BQC in the parallelogram. Now from Q, draw a line to BC perpendicularly, that may be QY. Therefore, here now we have drawn QY line perpendicular to BC, and also draw PX, that is perpendicular to AB. Now separately let us find the area of both the triangles, that is area of triangle APB will be equal to half times base, that is AB, times height here is PX, that is equal to half times product of AB into PX, that is equal to half times. Here in parallelogram ABCD, if we consider AB as base, then PX will be the corresponding height. Therefore, in a parallelogram, the product of base into its corresponding height is area of that parallelogram. Therefore, we can replace the AB into PX as area of parallelogram ABCD. Similarly, let us consider the area of triangle BQC, which is equal to half times base, here is BC, into height here is QY, that is equal to half times product of BC into QY. Now in parallelogram ABCD, if we consider BC as base, then its corresponding height is given by QY. Therefore, the product of base into corresponding height is given as area of that parallelogram. Here, the area of triangle APB and area of triangle BQC is equal to half times area of parallelogram ABCD. Therefore, finally we can say that area of triangle APB is equal to area of triangle BQC. This is what our proof required. Moving on to fourth question. In figure 9.16, P is a point in the interior of a parallelogram ABCD. Show that area of triangle APB plus area of triangle PCD is equal to half times the area of parallelogram ABCD. And second question, area of triangle APD plus area of triangle PBC is equal to area of triangle APB plus area of triangle PCD. Now moving on to solution. Let us consider the figure which is given here. Let us draw a line segment MN passing through P and is parallel to AB and CD. Now we came to know that MN is parallel to AB and MN is also parallel to CD. Therefore we can say here MN is parallel to CD, which is in written parallel to AB. Now let us consider in parallelogram ABNM, the parallelogram ABNM and triangle APB lie about common base, that is AB, and they also lie about two common parallels, that is MN and AB. We know that when a triangle and a parallelogram lie in between the common parallels and have a common base, area of triangle will be equal to half times area of parallelogram. That is here area of triangle APB is equal to half times area of parallelogram, here is ABNM. Let it be as equation number 1. Similarly, if we consider MN parallel to CD, then parallelogram MNCD and triangle PCD lie about the common base CD and in between the common parallels MN and CD. Therefore, here also area of triangle will be equal to half times area of parallelogram. That is area of triangle here is triangle PCD which is equal to half times area of parallelogram, here is parallelogram MNCD. Let it be as equation number 2. Now by adding 1 and 2 we get area of APB plus area of triangle PCD is equal to half times area of ABNM and half times area of MNCD. That implies area of triangle APB plus area of triangle PCD is equal to half times the area under ABNM plus area under MNCD. That is equal to half times area under ABNM, and MNCD is nothing but area of parallelogram ABCD. Therefore, area of APB plus area of PCD is equal to half times area of parallelogram ABCD. This is what our first proof and hence proved. Now let us prove for the second one. Consider the given figure. Here let us draw a line XY passing through P such that XY is parallel to AD. As XY is parallel to AD, it will be also parallel to BC, since in parallelogram opposite sides are parallel. Therefore here what we are doing is join XY through P such that XY is parallel to AD, and as AD is parallel to BC, we can say here XY is parallel to both AD and BC. Now let us consider AD is parallel to XY, then the parallelogram ADYX and the triangle ADP lie about common base AD and between common parallels XY and AD. Therefore, when a triangle and a parallelogram lie in between the common parallels and have a same base, then area of triangle will be equal to half times area of parallelogram. That is, here area of triangle is nothing but area of region under APD, which is equal to half times area of parallelogram, here is nothing but area of ADYX region. Let it be as equation number 3. Similarly, if we consider XY is parallel to BC, then the parallelogram BX YC and the triangle CPB lie about common base BC and between the common parallels, that is XY and BC. Now when a parallelogram and a triangle lie about the common base and in between the common parallels, then area of triangle, that is area of triangle BPC or CPB, will be half times area of parallelogram, that is BXYC. Let it be as equation number 4. Now let us add equation number 3 and equation number 4. Then we get area of triangle APD plus area of triangle CBP or CPB is equal to half times area of ADYX and area of BXYC. That implies area of APD plus area of CPB is equal to half times, here the area of ADYX and area of BXYC is nothing but the area of parallelogram ABCD. Let it be as some equation 2. Now from the proof 1 and here obtained equation 2, the LHS side, that is left hand side, is equal to half of the parallelogram area, that is ABCD. Therefore we can equate both, that is area of triangle APB plus area of triangle PCD is equal to area of triangle APB plus area of triangle, that is equal to area of triangle APD plus area of triangle CPB. This is what our second proof required and it is hence proved.